So in this segment, we'll give you an introduction to software testing. Again, for those of you who are familiar with software engineering techniques, this may be a little bit of a revision, although we'll try to focus somewhat on things that are unique to the medical domain. So let's offer some comments on testing. Software testing is not the same as software validation. Testing is really part of verification. We want to ensure the software was correctly implemented as designed. Validation goes one step further and checks that the user's needs are met. So testing makes sure the software works, but it doesn't tell you if we designed the correct piece of software. The software testing and processing involves different processes. We have automated regression testing. We can have interactive user testing. There are all kinds of techniques. And if you remember nothing else from this segment, please remember that testing cannot catch every error in the system. You can only test so much, and there will always be another bug. So just keep that in mind. So since we can't do that, what can we do? We have to face the basic asymmetry. We can never prove that the software is free from error, but we can prove that there are errors by discovering them. So you can never prove there are no bugs, but you can always prove that there are bugs. We find the bugs. And if we find no errors, all that we know is that the testers found no errors, which is not really heartening. So the goal here is to keep finding errors, but over time to see the number of bugs go down. So in the beginning of a project, finding a bug is a good thing. It increases the confidence in the software and the testing process once we fix it. But what you want to see is some sort of plot like this, where the number of bugs are plotted against weeks starts from a high level and sort of progressively drops down. If the number starts at the low level, that means our testing process is bad. We're not finding bugs. If the number of bugs stays high, that means we're not fixing them. What you want is some process where we have a lot of bugs in the beginning and progressively this goes down. This gives us confidence that our process is catching bugs and we're fixing them as we go. There are two fundamental types of testing. There's Whitebox versus Blackbox testing. So let's see what these things mean. In Whitebox testing, we do our testing using detailed knowledge of the structure of the code. So another way to think about that is that we can see inside. Black box testing, we have no knowledge of the internals of the software. We're testing it from the outside. Perhaps better words would have been transparent testing. We can look inside versus opaque testing. We don't know what's inside. We just feed inputs and get outputs, and that is black box testing. So you immediately realize here that when testing is done by programmers, it's often in the white box mode where we know the code and we write additional code to exercise pieces of it. When testing is done by outside testers, especially in the clinical setting, that is more of black box testing. They don't know what's inside. They're testing, if you provide this input, what is the output that I get? A key problem in testing, and this is mentioned by the FDA in the GPSV, and that's the code in the purple box there, is the so-called multiple path problems. So here's a little simple piece of code. I think we've seen this before with two inputs, A and B, and depending on the value of A and B, we can go down different parts in the code. And because even the simplest piece of code will involve many of these branches which exercise different parts of the code, A plus B plus 4, A plus B plus 6, A plus B plus 2. Even a simple piece of code requires a significant amount of testing to ensure it. And let's go back to that code. Unlike some hardware failures, software failures often occur without advance warning. This is because software can follow many paths due to branching statements, some of which may not have been fully tested. So we may have only tested these three endpoints of the code. Suddenly we find ourselves over here, and all of a sudden we find a bug that just appeared because we have just applied the conditions to the code. This happens. And if you can see that this trivial piece of code has 4 outcomes, you can imagine something more realistic, more complicated. This can go on and on. So one of the advice that people give is that you want to reduce the complexity to allow for testing. So if you have too many permutations, too many features, too many options in the code, this makes testing hard. So to give you an example, if instead of having a value from 1 to 8, that you can set 1, 2, 3, 4, 5, 6, 8, you reduce it to low versus high, all of a sudden you have cut down 8 tests into 2 tests, and that's a good thing. It simplifies your code. They often arise from the software having extra functionality, things that the programmer thought we needed, but not necessarily needed by the user. In mission-critical cases, we eliminate complexity to reduce it to the smallest feature set possible, and that is a critical point. Look at your software critically. You have a certain set of needs, you have specifications. Just review those with a very clear. Are all these things really needed? Are these things we must have? If not, maybe you can reduce some of those things and it will make your software easier to test. Eliminate complexity, code the simplest, smallest thing you can. That will make your life a lot easier. And experienced developers always aim for the minimum number of features. And Code that has a small number of features is going to be more conducive to comprehensive testing. And unless you can test your code, you don't have code that works. So having code with more features is not better if you can't test all those features. You should only have code that you can test, that you can trust. And this sort of concludes the operation, you code with the testing in mind. Can I test this piece of code? If we can't, then maybe we shouldn't code it. It's not going to function. What is software testing? Let's look at a formal definition here from Vogel. This consists of a number of steps, but let's look at them. It's an activity in which a system, subsystem, or individual units of software is executed under specified conditions. This is the first step. We run our code under some conditions. The expected results are anticipated from requirements of design. If we have a piece of code that adds two numbers, we give it two numbers, we know what the result is going to be, because from design we know what the answer is. The actual results are observed and recorded. Now we run the code with those inputs and we get the result. And an assessment is made as to whether the actual results are acceptably equivalent to the anticipated results. And if they are, the test passed, and if they're not, the test failed. This is a formal process. Let's walk through it in a slightly simpler form. So we specify the conditions. These are the inputs. So if this is our branching problem, we have A and B. Those are our inputs. The expected result, well, we can mentally read through the specification and say, well, if A is greater than 2 and B is less than 4, the result is A plus B. We know what the result is supposed to be. We run the software and we record the actual results. And then we perform an assessment. We compare the actual versus the expected. And if these are close enough, we declare the test to be a success. Now, sometimes close enough could be that, in a simple case of addition, it has to be exactly the same. Sometimes close enough may literally be, well, if it's less than 1% different, we call this good enough. Sometimes we're running a nonlinear optimization on different hardware. And because of rounding errors and different processes, you're going to get slightly different results. So you have to ask yourself, what is good enough? Sometimes we compute a correlation. Sometimes the error is less than 1%. Those are all driven by experience of the particular situation. There are different levels of testings, and you'll see this pyramid appear here. We have unit testing. These are the smallest pieces of code that do a specific task. We have integration testing. This is where we check for the communication between the pieces to ensure that information gets transferred appropriately. And we have system-level testing. We check the whole system from the perspective of the user to make sure that it does the big tasks. So let's, again, look at it more graphically. So this could be our software. The green box is the system. The system consists of a set of modules. These are sort of these yellow things. And this module consists of a set of units, the smallest boxes in the middle. So we can have unit testing, checking this level. We could have module testing. It's like unit testing plus, to check these bigger things. We can have integration testing. We check the communication along these lines. And we have a system level testing where the system as a whole is tested. So let's look at unit testing first. This is Whitebox testing. Often this consists of automated regression tests written by the developer, and the goal is to exercise the units over a range of inputs to ensure correct behavior. The word regression here comes from the fact that you run the test, you get a number of results, you run it again the following day, you get the results, and if anything changes in between, you can also tell if you've made any difference in the code that broke something. So part of the goal of automated regression testing is to see that if any change that we've made has broken something into the software. The other thing that regression testing is extremely useful for is if there's an operating system update. Has anything broken? Is anything that the system provides to our software changed such that now our code is suffering from it? So this is regression testing, and good projects will run this every night and just get a list of tests the following day and just keep track that nothing is breaking the code. The comprehensiveness of Whitebox testing involves understanding the structure of the code. Now, we need to look inside the code. How many tests does any given thing? So let me give you an example. The following needs at least 2 tests. So if input is less than threshold, do something. Otherwise, do something else. So here we need 2 tests, something where the input is less than threshold, so we can exercise this function, do something. And then another test where the input is greater or equal to threshold, so we can exercise this function, do something else. If we only have one input and we only exercise one of those 2 functions, we have an untested piece of code that may manifest a bug at the worst possible time. So here's some caveats, some issues with unit testing. The first thing, and this is obvious until you think about it, but not so obvious until you think about it, this comes from Vogel, all testing code is code. There will be bugs in your testing code. So for example, a particularly dangerous bug is that all tests pass because it's a bug that fails to detect test failure. The solution, And the one I like is to have some tests that are designed to intentionally fail, and this allows us to test the testing code effectively. And complex code is harder to test as there are many paths through the code. The solution here is to break up into smaller units and test it separately. So always simplify, always keep things up. Vogel has this code that says that if there are, you have to remember that even the code that's written for testing is code, and it can actually fail. And if there were never any bugs in the testing code, if you had people who could write that perfectly, you should have those people write the original software, and then you can dispense with the need to test it because we have people who can write perfect code. There is no code that is error-free if written by humans. All code is written by humans. So you could have bugs not only in your original code, but in the code that's written to test the code. And I know it becomes sort of this recursive no-end process, but you have to be mindful of that as well. The next level up is integration level testing. Here we focus on the transfer of data and control across a program's internal and external interfaces, how information is transferred from module to module. We could have external interfaces, other software, including the operating system, hardware, the users, and often this process involves creating simulators of this external software and hardware to provide inputs and to consume the outputs. For example, in a project I'm going to talk about in the next segment, where we did real-time fMRIs, we had a real-time fMRI system, we created a mock MR scanner that provided data in so we could test the system. And we'll come back to this in the next segment. And then there is system-level testing. This tests the software as a whole, and it proceeds from the system design and ensures that the software behaves as needed. This benefits from randomness. You can tell your testers to play around and see if anything breaks. There's a medical analog to this. There's something called random and targeted biopsy in prostate cancer. So in prostate cancer, in the way it's done with fusion biopsy, as in the example we showed in week 5, we do an MRI. We have some lesions that we're suspecting of cancer. So the urologist will target those directly. But then they will also do some random testing. They will take samples from different parts of the prostate just to see if they're missing something, if there's cancer that's not visible in MRI. Same applies to software testing. You do some testing that are prescripted. These are the things we absolutely must test. And then you tell your tester to do a little bit of random operations. Something might break, you might find something. You cannot have a comprehensive test, so some randomness helps here. And then there's something called smoke tests. You just simply try to do something with the software and see if it works. This is by analogy to sort of car engines. You turn the car on and see if any smoke comes out. If it doesn't, we're probably doing well. The huge benefit of this is that they involve the actual software, not some small program linked to the code. And ideally, you use self-testing to test the actual executable via some sort of command line switches. An example of a project which does this significantly is 3D Slicer, a very well-known package for medical image analysis. And we have a little clip from Dr. Steve Piper, who's the lead maintainer of this, to tell us about it.
It is interesting, and there are taxonomies, and if I try to quote them verbatim, I'll probably get them wrong. But there are, as you say, there are unit tests, and there are integration tests, and there are smoke tests, and there are ways of thinking about testing. But the one that, in the end, I tend to, and you can't ever do enough, right? As many tests as you write, there always should be more. So then you have to ask yourself, where do I get the most, return on my investment? And that's where I think smoke tests and unit and integration tests are probably, a worthwhile thing to do. And in particular, I consider the self-test kind of the pinnacle of that taxonomy, mainly because, as you mentioned, it uses the actual executable in the way that the user would be using it.
And that is the point here. That is the benefit of using the whole system level testing in self-test mode. You're using the executable, not a small piece of code that may not be linked to everything, that the initialization doesn't happen properly. You're trying to simulate the user environment as much as possible. There's no substitute for the real world, but you want to get as close to it as possible. And the system level testing, especially in self-testing mode, lets you do that. The final piece of testing, and this is where we have users do the testing interactively, is that we use scripts. And by scripts here, I mean in the theater sense. We give a user instruction, say, follow these steps. So let me give you an example from some of our own software. Go to the File menu and load your own image by clicking the Load Image button there. Does the image open? Yes, no. If no, you mark it as a failure. Does the Paint Tool menu appear? Now that you have an image, maybe the Paint Tool appears. Do numbers appear at the bottom left on your screen? These numbers inside the parentheses indicates the coordinates of your location. If you click Viewer Control on the right side of the screen, does a Viewer Control menu appear? And these are just steps that we ask the user to follow as we go through the process. And often they fill in a spreadsheet with yes, no, and we collate them. on different platforms on different days to make sure nothing fails. So there could be one last step here. You click on the blue Z plus and Z minus buttons, and there's the image zoom in and out. And you can have all the automated tests in the world, but at the end of the day, you want actual users testing your code, because human interactive testing can also find things. They can see a glitch, they can see a flash on the screen, whereas a computer is only concerned about the input and the output. A human can often tell you other things that are useful in the process. A good tester will always find something to complain about, and you should treat testers that complain well. They're the most valuable testers you'll ever have. So this concludes our introduction to testing. In the next segment, we'll zoom in and talk about integration testing in the context of real-time fMRI. Thank you.